Okay, so I think we can start. Yeah. So yesterday we started talking about subset simulation. We talked about the fundamental motivation, how you can decompose a small failure probability as product of larger probabilities, and all of those stuff. And we kind of ended with the algorithm, but in algorithm there is a step that is kind of missing, or rather there is a step that I did not discuss, which is how to sample from the conditional distributions, right? So today primarily we will be focusing on that only. But that conditional distribution sampling is in reality carried out by using Metropolis Hastings algorithm, which is a type of Markov chain Monte Carlo. Okay. I will not be talking details about Metropolis Hastings algorithm. So for that I will refer you to my previous recorded lecture last year this time on probabilistic machine learning, and there I have taken, if I am not wrong, 3 lectures on this Markov chain Monte Carlo. The first lecture was on Markov chain, the second lecture was on Metropolis algorithm, the third one was on Metropolis Hastings algorithm, and each lecture was 1.5 hours. So go through that 4.5 hours of lectures to understand the Metropolis Hastings algorithm and the working principle of this. Today I will just be talking about the subset simulation aspect of Metropolis Hastings algorithm without diving deep into the actual details of Metropolis Hastings algorithm, what is irreducibility, what is aperiodicity, and all those things are there in Metropolis Hastings. For that you please refer to probabilistic machine learning that I taught last year, 3 lectures, Markov chain, Metropolis algorithm, and Metropolis Hastings algorithm. Okay, so this again will count as your self-study component, by the way. Okay, clear? Okay, coming back. So we were talking about subset simulation, and the basic principle of subset simulation is that you will probability of failure, you will write it as product of f1 f2 given f1 and then until probability of fm given fm minus 1, right? This is the decomposition, the Markovian kind of decomposition, where f1 f2 these are some event, they are not the failure event, they cannot be the failure event. Fm, that is the actual failure event. Okay, so this corresponds to the Fm corresponds to failure, and we discussed it yesterday, nothing new. And for this kind of setup, the assumption is that F1 is a superset of F2, this is of Fm, right? So this is the setup, and this Fm is actually equal to the failure event. This is the failure event. Okay. We said one more thing, that this F1, F2, these events are decided by us. We can always decide those events such that each of these events have approximately equal probabilities. So we said that setting probability of f1 is equal to probability of f2 given f1, again not equal to, I think approximately equal to I should write, but anyways, is equal to probability of, what was the last one? M minus 1, not m, that will not hold, right? F of m minus 1 given f of m minus 2, and that is equal to, let's say, p naught. Okay, that is equal to p naught, and the standard value of this p naught is 0.1 or 0.2. It's a hyperparameter, you need to check that for your problem what value of p naught works, but generally it has been observed 0.1, 0.2, 0.1 mostly are reasonable values for p naught. Okay. Okay, With this assumption, you don't need to find the probability again and again. The product will become easier. That product actually you don't need to do in essence, right? And the other thing is that is helping you automate the algorithm. Otherwise, how will you decide those things? Lastly, the number of samples at each level that can be fixed because of this are same. If one is 10 to the power minus 3, other is 10 to the power minus 1, then that n should accordingly vary, and that's a headache, right? So all of those are the reasons. So F1, F2 given F1, yes. And then we saw that the last thing yesterday, I mean, last formula kind of P naught to the power m minus 1 multiplied by failure points by n, right? And failure points, this corresponds to Fm given Fm minus 1, right? Now let me write the algorithm once more, because there are certain automation thing that I did not mention because we were ending the lecture yesterday, and then we will go into the determination of this conditional distribution, or rather how can you sample from this conditional distribution. But writing the algorithm once more is important. Okay, so algorithm. What are the inputs? Remind me. P naught, n, PDF, and I think that's all, right? What was step 1? Sample x from the PDF. So xi, you are sampling from fxx, where I goes from 1 to, let's say, n. What was step 2? You will find out the limit set. Yi is equal to g of xi. Again, I goes from 1 to n, right? Step 3, sort in ascending order. Okay, sort, I am writing y now, so y should include y1, y2, y3, yn. So sort y in ascending order and find, I am combining the next step from yesterday, and find the threshold. And how will you find the threshold? P naught is given to you. P naught multiplied by n should be the index. So y at the index P naught multiplied by n, right? And find threshold. Let's call it B0, or maybe B1 is better. B1, which is equal to y P naught times n, and this should be, so let's just something like this. Okay, and by the way, when I'm writing y, this y is already arranged in the ascending order, so maybe I should write ya. Ya is basically y arranged in ascending order, right? And okay, so I will make a small notation change here. Let's see what I am doing. I am writing here x1 and y1, okay, and I will write it inside a bracket so that it does not seem like a okay. So 5 minutes. Don't waste my time and the class's time. So sort y in ascending order and find b1. Okay. So why did I write x in subscript 1 inside the bracket? Any idea? Iteration, not exactly, but level, I will say, because this is corresponding to f1. I will also draw sample of x corresponding to f2 in this decomposition. Now, sample that I draw corresponding to the event f1 will not be the same samples that I draw corresponding to f2. Those samples will change, right? So to distinguish that they will change slowly, we introduce this 1 into picture. Okay, because otherwise, let us proceed and you will realize what will happen. Okay, so this is done. 4. What will you do? What do we do in 4? Step 4. Select samples that belongs to f1, the event f1, and f1 means failure. And not failure, I mean which are less than this threshold, whatever it is. So this is select x1i corresponding to which y is less than threshold. So threshold should be here less than 0, right? Y is less than b1. Is this step clear what I did? So suppose I have 100 samples. Out of that 100 samples, because I am using 0.1, 10 samples have failed. So I am taking the x values of those 10 samples corresponding to which y was less than b1. Now y less than b1 is actually not failure. This is like pseudo failure that I am introducing to the system. But actual failure will only happen when y is, I mean gy is less than 0 or something like that. Gx is less than 0, right? Gx is less than 0. So keep in mind that b1 is not your actual failure. It's an artificial event that I am creating because I want to increase the probabilities. Okay, clear? Select these things. Step 5, what will you do? Step 5, remember, at this step you are already done with computing P of f1, right? Step 5 should now focus on P of f2 given f1. So you need to draw sample from the event f2 given f1, or you need to draw samples x such that f1 holds. Correct? That's what you need to do. And that you cannot do directly. You cannot draw samples from this conditional distribution directly. And I will tell you why in a short while. You cannot draw directly. So what you will do is that you will form a Markov chain corresponding to the event f2 given f1. And you will use that Markov chain to draw sample. Okay. So using x1i as seed. Seed means they are the initial samples. Okay. So we will use the failure sample from the previous step as our initial sample for this step. Clear? So using x1i as seed. Seed means initial sample. Form a Markov chain for f2 given f1 and draw samples. Okay. This samples corresponds to which event? f2 given f1. This sample should not correspond to f1. So this is like my level 2. So now I will write x2i. Right? And these are coming from which distribution? F of x given f1. Why x given f1? Because x is the variable, PDF of x. Given f1 has already occurred. Because it was f2 given f1, but f2 is the event, x is the sample, so PDF of x given f1 has already occurred. Okay? So you will draw samples from this distribution. After that, you will follow the same steps. So after that, what will you do? You will find out y, 2i. You will sort it. Based on the sorted number, you will select p0 times n. And that will give you your B2. Right? Once you have your B2, you will be using the B2, you will select x2i corresponding to which failure has occurred. I mean pseudo failure again. And that will begin your step 3. Clear what is happening here? Again, I am assuming you can draw this sample for now. Okay. So step 6 is you have xi, so it will become y2i g of x2i. Step 7 will be sort y2i or y2 should I write maybe in ascending order. You will sort y2 in ascending order and find B2, which is equal to the sorted version. So y2a, let's call it, I think previous one I should write y1a somewhere. Yeah, y1, here should be 1a, right? So y2a and then p0 times n. Okay. And then basically what is the next step? I mean, select, basically I can just say that repeat step 5 to step 7, right? Repeat step 5 to step 7. The question here is, until when will you repeat? Can you tell me? Yesterday someone was asking after the lecture that we should repeat until when? How will you know that? Because it's a computer code, you will not see that, right? So how will your code know when the actual failure is coming? Is 0. So every time you are taking threshold, and what do you think every time the threshold will happen? It will keep on reducing. So if the threshold, sometime you see that you take p0 time n and that is going to negative value. What will you know? That no, this time I should not do that. I should only take, this is my last step, and I should only calculate the failure points until 0, divide by n, and that is my last step. And right? Before that you have counted how many times you have done that, p0 multiplied by that to the power, p0 to the power m minus 1 multiplied by nf by n. I will repeat, each time when this algorithm is running. So let me write one more thing actually very quickly. So this steps corresponds to level 1, right? This step corresponds to level 1, which is sampling from f1 or sampling corresponding, basically directly sampling, no conditional. Step 5 to 7, including the repeat, corresponds to level 2, level 3, level 4 until m minus 1. But this m minus 1 will also come out automatically, and that is why we are, you see this B2 we are calculating, but we are actually not using it till now. I calculated B1, right? But what was I using B1 anytime? I wrote it that y less than B1, but do I even need that? I know that P0 type n is the samples, I'll directly take those x. right? B1 actually I do not need, but I am storing the B1. The reason is that I will keep on tracking that B1 or B in this case, and if that B goes to negative, I know in this case I should not take P naught time hence. I should stop at 0, less than equal to 0, find the number of failure points, whatever there is, and that NF by N will be the probability of that level multiplied by P naught to the power M minus 1. Okay. This is clear for everyone. M, N value. N is function of what? Probability of failure. If you and what is the probability of failure you are calculating here? 0.2 or 0.1? For P naught, right? It is, you are doing it at each level, and each level it is P naught, and in the even at the last level it will be close to P naught only. So for that P naught you can find out what is the N. Clear? People have used 500, 800, 1000. That's a standard level of N in subset simulation. Okay. Any other doubt on this one? This whole algorithm is clear, right? So repeat step 5 to 7 until B naught becomes, until B naught is positive basically, or not B, I should write B, not B naught, B is positive. Okay. If B becomes negative, then you should stop repeating it, but you should do it this step one more time. But this time you don't need to arrange it and all those things. What you will need to do is that you will just need to calculate the failure and divide it. And after that, you will again, step 8 will be step 5. Step 9 will be step 6. Step 10 will be whatever I call it, let's call it PM hat maybe, is equal to NF by N, right? And your final PF is equal to P naught to the power M minus N multiplied by NF by N. Clear? When you write the code, there is one if loop, if condition that will be there, where it will check every time that whether that B is going to 0 or not, or less than 0 or not. If it goes less than 0, then be careful, it should break that, do it one more time and stop, right? So when you write your code, this is something you need to keep in mind. Any doubt on the algorithm, apart from how to sample from the conditional? That I will anyways discuss, but any doubt in the algorithm? Please go through the algorithm once more. I'll give you 10-20 seconds and let me know if there is any doubt or any step that is not clear in the algorithm. Okay, so please, you have taken notes, so please go through it. I will change the slide. Okay, how to sample from f x given fi, let's say a generic one, right, where I can change. Yeah, so any doubt? No? Threshold selection, right? You want that the probability should be equal to P naught, right? Which means out of n samples, n P naught samples should fail, right? Assuming your failure condition is less than equal to, assuming less than equal to, once you have arranged in ascending order, which should be your threshold? N P naught element in the ascending order, that's what is the threshold. If you assume it is less than, then it should be +1. So in some book it can be +1 also, that's okay. I mean, it will not matter if it is in 500, if it is 50 or 51, it will not matter that much. Okay, but clear what is happening? So this is the thing, and this way you will calculate threshold every time. Last time, if you see that it goes to negative, and this is your question yesterday, right? Exactly. If it goes to negative, assuming gx less than 0 is failure, obviously, that's an inherent assumption I'm making. In that case, you should not do it for that. You should not find out, take it to be P naught, but rather you should calculate. Clear? Any other doubt on the algorithm? It's clear? Okay. So if it is clear, let us proceed to how to sample from f PDF. Remember that PDF of x conditioned on that if I has already occurred, where I can be 1, 2, 3, 4, anything. Okay. So we'll talk about this later. You tell me, assume 2 events. So consider 2 events, A and B. Okay. So in this case, from product law, what is probability of A given B? P of AB or A intersection B divided by P of B. All of you know about it, right? Let us write it. P of A intersection B divided by P of B. Okay. Can you tell me, now suppose I introduce a random variable x here. A and B are events. A and B are events. A and B are not random variable. Let us introduce a random variable into picture. Okay. So suppose x is a random variable, and if it is a random variable, it should have a PDF or PMF, depending on whether it is continuous or discrete. We are working with continuous, so I'll assume continuous, so it has a PDF. Is a random variable with PDF fxx. Okay. So can you tell me with this setup, what is probability x belongs to A given B will be equal to? Same thing. I'm looking at probability. It should be exactly same thing. It should be probability that x belongs to A intersection B divided by probability of B, because that event has already occurred. So same thing. Now, what is the numerator? Can you compute it using PDF? How will you compute the numerator using the PDF? How do you compute probability using PDF? Integration. So you will do a integration of the PDF. In which range? In which range? If you do from minus infinite to infinite, it will give you 1. So in which range? In the range where minus a what? Why minus infinity to a? A is not a number, A is an event. Keep it in mind. So A can be something like minus 2 to 3, anything between them. It can be like that also. So in what range? In the range where the event holds. And what is the event here? A intersection B. So you should integrate it in the range where the event holds, which is A intersection B. Correct? Everyone follows? So this should be in the range A intersection B divided by P of B. Okay. Now let us draw a Venn diagram. Set theory Venn diagram you are aware of, right? If I draw a Venn diagram, let's say this is my event A, this is my event B. Okay, this is A, this is B, and you know the intersection is A intersection B. So if this is the scenario, the event space of A and B, then you are actually integrating in which area? This area. You follow that? Can you think and tell me, I want to change this integration area to A only. I want this integration area to be A. I do not want a B in the integration area. That means I want to integrate over this whole area. Right? How can I do that? How can I mathematically write that? The question is clear? I want to write this integration fxx dx, but I now want to integrate over A, but I should get the same result as x belongs to A intersection B. So what can I do? I'll give you a clue. Think about using indicator function. Give me the expression. Remember, I told you what I want to do. I said I want to integrate over A, fxx. This is what I want to do. Correct? That means I should multiply it by something. I of what? I of x belongs to A. B. A or B? B? Correct. It should be indicator function of B. Think what will happen. You will integrate over the total area. But whenever it is not in this A intersection B area, in this case, this I will give you 0. So although you are integrating over the whole A, practically you are integrating only in the A intersection B. I'll repeat it once more. See, this fxx you are integrating over the whole area of A. So that means over this whole area it is getting integrated. But when you are in this area, what is the value of IB? 1, because that is also belongs to B. Wherever you are in this area, what is the value of IB? So practically which area you are integrating over? A intersection B. So I can write it in this manner. Clear? You can do that? Okay. Divided by PB is there, by the way. Clear? Now another question. Same thing. I want probability of x. I want probability of x belonging to A given B has occurred. Okay. I want to write it in terms of PDF. I want to write it in terms of PDF of x given B. How will I write it down? X given B means it is the conditional PDF of x, the random variable, given B has occurred. So if I know the conditional probability distribution in this case, or conditional PDF of x given B has occurred, then how can I write it by using that? If the conditioning was not there, how would I have written it? No, there is, why do you need a, I am saying assume that B is not there. X belongs to A. Let's first assume that. I want to find probability x belongs to A. What is, how do you find it out? Integration fx dx in A. Now there is a conditioning on B. The rule does not change, it is the sum law. Right? What will you do? It should be simple. Same thing, but the PDF should not be fx. The PDF should be fx given B. Because your event is now given. This should be equal to integration fx given B dx over A. That's the basic law of probability, that if you have a PDF of the exact event, then integrate it in the zone you want to find the probability for. In this case, you know the exact PDF of x given B is given to you. It's given, right? So if it is given to you, this is what you should do. Clear? Now if I compare these two things, this is also giving me x given A comma B, A given B. This is also giving me given a comma b. X belongs to a given b. If I compare these two expressions, this one and this one, what can I say? So therefore, f of x given b is equal to f of x multiplied by indicator function in b of x divided by probability of b. So knowing the PDF of x, I should write a x here, I should write a x here, but yeah, knowing the PDF of x, you can find the PDF of x given a event b, let's say x given b, by using this formula where you need the PDF of x, which is generally known to you. You need an indicator function, which you can always define, but you will also need probability of b. Correct? And if you know these three things, you can find the conditional PDF. Okay. So now let us use this formula for our case. In our case, I want to find the probability of x belonging to f2 given f1 or fi given fi minus 1. So using this, probability of x, which is my random variable, belonging to fi given fi minus 1 will be equal to what? It will be equal to fxx I fi minus 1 x divided by probability of fi minus 1. So do you know everything from here? fxx obviously you know, that is the PDF. Indicator function I you can always define, so you know that. But probability of fi minus 1, is that known to you? You do not know that. You know probability of fi minus 1 given fi minus 2. You know the conditional probability that you have defined or derived in the previous step, but you definitely do not know what is probability of fi minus 1, right? Because you have not calculated it. So that means this is proportional to, but that will be constant, that you can acknowledge. Given that that has occurred, that will be a constant. So this is proportional to fxx I fi minus 1 x. So probability of okay, I wrote something wrong, right? This is wrong. This is not the probability, this is the PDF. This is the PDF, right? Look at the left hand side. This is what? F of x given fi minus 1, right? It's the PDF. So therefore, what we arrived at is PDF of x given fi minus 1 is proportional to fxx I indicator function fi minus 1 x. Is it clear? This is clear. Now comes the Metropolis algorithm into picture. Metropolis algorithm, Markov chain, Monte Carlo, which is a broader thing, or even rejection sampling. These are all algorithms that allows you to sample from an unnormalized distribution. Remember, this distribution is not normalized. It's an unnormalized distribution. What do I mean by unnormalized distribution? If you integrate it, you will not get 1. You will get P of B or P of fi minus 1. If you integrate it, you will get P of fi minus 1. And that way it will cancel out. That's how it will, right? So this rejection sampling, there is a variant of importance sampling also, to be very honest, that I have not covered, but it is there, because that I generally cover in machine learning. in this course it is not needed. So then Hamiltonian Monte Carlo, Markov chain Monte Carlo, and inside that Metropolis testing, Metropolis algorithm, all of these are sampling techniques that allow you to sample from an unnormalized distribution. Out of that, the most popular one historically is the Metropolis testing algorithm. The Metropolis testing algorithm was one of the top 10 algorithms of the century from 1900 to 2000. So there was an article that came out and it listed down 10 most popular algorithms of that century. Metropolis testing was one of those. Others, expectation maximization was one of those. Fourier transform was one of those. Others I don't know. Okay, but this is one of the top 10 Metropolis testing, not subset simulation. Metropolis testing is one of the top 10 algorithms of the previous century. Okay, and it allows you to sample from unnormalized distribution. So we use Metropolis. By the way, I am writing Metropolis testing, but what we will use is actually Metropolis, because in our case Metropolis testing and Metropolis will become identical. Okay, Metropolis testing is a generalized thing. Metropolis testing algorithm. Okay, but there has been recent paper which has used Hamiltonian Monte Carlo also with subset simulation. So there have been papers like that. Okay, so it's not that you can only use Metropolis testing algorithm, but the original subset simulation proposed in 2001 by the same person who proposed importance sampling for rare event or reliability, S.K. Au and Beck. Actually, there were two researchers. I think S.K. Au was a PhD scholar and working under J.L. Beck, and it was part of his PhD work at that time. So they came up with this, both this subset simulation and importance sampling in the context of reliability, because importance sampling was already existing. Subset was new, but Metropolis testing was already existing. So in the context of reliability, they are the one who came up with this, both the algorithms, S.K. Au and J.L. Beck. Okay, Au and Beck, popularly known as. So they used Metropolis testing or Metropolis in the original implementation. So we are talking about that. But recently there have been approaches which has used some other algorithms also. Okay. So how does the Metropolis testing algorithm work in our case? Okay. So the algorithm, I'll remind you that you should read about Metropolis testing algorithm on your own. What I told earlier is that in the probabilistic machine learning course that I taught last year, and that has been recorded, so it's available. There are 3 lectures that I've taken on this topic. The first one is on Markov chain, the usual Markov chain. The second one is on Metropolis algorithm. Third one is on Metropolis testing algorithm, and each of that is 1.5 hours, because that was a 1.5 hour class. So go through those 4.5 hours of lectures. Okay, and that will basically help you build knowledge about the Metropolis testing or Metropolis algorithm. Okay, here I am only going to write down the algorithm without deriving how this algorithm is coming into play. There, with schematically, with intuition and derivation, everything is done. Okay, so algorithm. The algorithm starts with, it will start with what? It will start with something that I've already mentioned here. See, using x1i as seed. So the samples you have generated in the previous step, the failure samples, will be your starting point. That's what I've written, right? Using x1i as seed. So that means the failure samples at your previous level. I wanted to use this term level, that's why 1, 2 came into picture. So the failure points in the previous level will be used as starting seeds. Okay. So algorithm, it starts, again, I'm using the term failure, but keep in mind pseudo failure. It's not a real failure. I'm reminding it because you should not get confused. So starts from samples in previous level. Okay, and you should start from each of those separately and then collect samples. So in metropolis testing, it's a kind of rejection sample. Okay, although you never reject actually, you reject, but still the chain goes on. But it's in some sense it's an improvement over rejection sampling. So what you do is simple. Step one is that, okay, this start samples in previous level. So let's call it, I have to give some name, right? Let's call it X level I minus 1, let's say. Because right now in the current level I will call it I. Okay. So step one, you have something known as the proposal density. Proposal density is a density from which you can easily sample. Okay. The most popular proposal is the random walk proposal. Okay. The random walk proposal, it is said, was developed by observing a drunken person. How? If someone is drunken, you are at a position, you can go any direction, right, randomly. If you are not drunken, you will walk probably straight. But that drunken person can go anywhere, given the current location. So that means that's a noise kind of thing. So in random walk proposal, to the current sample, you add a small noise or a small sample drawn from a zero mean noise or zero mean thing. Okay. So what you do is simple. You sample X star. X star is a proposal sample which might be accepted, might be rejected. From Q of X given X I minus 1. Okay. And this can be any proposal. The most popular proposal is the random walk proposal. Okay. So potentially random walk. Which basically means that your X star is equal to Xi minus 1 plus epsilon, where epsilon is drawn from a Gaussian with 0 comma sigma square. And this sigma square is a hyperparameter which you will decide. If it is very small, it will be taking long time to converge, lot of samples. If it is very large, it might go anywhere. Okay, so it has to be, it needs to be some optimum value, sigma square. Okay, and yeah, so there are some thumb rule kind of thing. So you draw X star. Step 2, you compute something known as the acceptance ratio. Compute A X star comma X I minus 1. And acceptance ratio is equal to minimum of 1 comma the ratio of your distribution, the distribution from which you want to sample. What is the distribution from which we want to sample? No, the right hand side. I want to sample from Fx evaluated at the proposal multiplied by I Fi minus 1, right? Yeah, Fi minus 1 X star divided by F x x Fxx the previous sample, right, I minus 1. Why am I not writing the indicator function in the bottom? There is an indicator function in the bottom as well, right? If I'm doing the ratio of the distribution has an indicator function. That should be there in the denominator as well. I'm not writing it. Why? No. We have selected xi minus 1 such that those are the failure points. So that means it will always belong to fi minus 1, which means your I will always give you 1. That's why I'm not writing it. You can write it, but it will always give you 1. Yes. That's the ratio. What is this ratio giving you? Even without going into the mathematics, can you tell me what is it giving you? It is giving you ratio of frequency, right? It is giving you ratio of frequency. If there are 2 points, x star and xi minus 1, which is more probable? That's what it is giving you. That's why it is called acceptance ratio. Intuitively, you should be able to appreciate that this is basically nothing. It's a PDF. And there are 2 points. You are finding the amplitudes. Unnormalized, that's okay. Do a ratio because normalized and constant will cancel out. And it's like out of these 2 points, which one is more probable? That's what it is giving you. That's why it is called acceptance ratio. The intuition is clear? Derivation, 4.5 hours of lecture. Go and check it. Okay. The indicator function, I am not writing it because it will always be 1. Okay. And then, if you are very lucky, let's say, this ratio will go more than 1. In that case, whatever sample you have generated will be accepted 100% of the time. But that will happen rarely. So, what happens if this ratio is 0.6? What should you do? If this ratio is 0.6, should you accept, should you reject, what should you do? If it is 0.4, you should accept, reject. If it is 0.5, accept, reject, you do not know. Actually, you know. If it is 0.6, then out of 10 times, 6 times it should be accepted. If it is 0.4, out of 10 times, 6 times it should be rejected. If it is 0.1, 9 times it should be rejected. That we know. For a given one, I don't know, it's random. But probabilistically, we know what could happen. So how will you ensure this thing, that if it is 0.6, then 10 out of 6 times it should be accepted? How do you think I can do that? I have to do something probabilistically, right? This is what we do. You also draw a sample uniform from u 0, 1. So this sample will lie in 0 to 1. And then if u is less than a, that means your acceptance chance is higher than this sample you have drawn, then you will accept. Accept means you will set x I is equal to x star with probability. This probability is just being written for completeness, but with probability a x star comma x I minus 1. Okay. And if u is, else, let's write else you do not reject, I told you. So xi will be equal to xi minus 1 with probability 1 minus a. This is the Metropolis testing algorithm. In subset simulation, you will do it for each of the level except the first level. And within each level, you will do it starting from each of the failure samples from the previous level. And from there, you will now select n samples. I'll repeat. In subset simulation, you are supposed to do it for all but the first level. And not only that, in each level, you have n or n p naught times n failure samples. Less than b1, less than b, right? P naught times n failure samples you have. So each of those should be your starting point. From there, you should do it, form this chain. And from those chain, you should select n samples ultimately as a combination of all those, because that n will remain constant. Okay. These smaller details will become more clear when you write the code, which will be in homework 3, which is after your minor. Okay. Because this thing you will probably follow, you will have an intuition, but the exact details you only learn when you write down the code. Okay. So yeah, so this is your Metropolis testing algorithm, which allows you to sample from the conditional distributions. Okay. One thing, this U part is clear or not? Is it not random? If it is 0.6, are you not supposed to select it probabilistically that only 60% of time it should be accepted? See what will happen. Why did I do it? Suppose A is 0.6. Okay. U greater than 0.6, how many times it will happen? 0.4 times, right? So that means if you do repeat this 100 times, how many times will your same sample be accepted? 60 times. That means the acceptance ratio is being respected. It is a random sampling strategy. Every time you run, first time the sample that was accepted, next time that sample can be rejected. It's stochastic in nature. Okay, there is randomness in everything, random walk and everything is stochastic here. This acceptance is also stochastic. That is because the acceptance ratio is 0.6, which means that if you do it 1000 times, you should only accept the same number 600 times only. Now you draw u 1000 times between 0 and 1. You know that because it is uniform, less than 60% will come 600 times approximately, and more than will come 400 times approximately. So when you use this criteria, it ensures that the sample is accepted with the acceptance ratio probability. The intuition is clear now? Or any doubt is there? I'll have to stop now. So if any doubt, we can talk after the class. Okay. Thank you.